Hi everyone, today I would like to talk about my package AutoHMM. I posted a video actually a week ago almost about hidden markup model, when to use it and why it's such a powerful algorithm. Today I want to go over this package that I wrote, AutoHMM. So what does this package do? Let's take a look at this package in the description of this GitHub repository. So AutoHMM says hidden markup model. This is if you would like to donate, right? And the auto HMM is an automatic, discrete, and continuous HMM. What it means is that this is what it does. So if you're using this package, please cite this paper. This is what I wrote during my PhD. But what this package does is that it's first of all, it's written in Python. Well, what it does is that it automatically finds the optimal number of states, no matter whether you have a discrete or continuous supervised or unsupervised hidden markup model. So what it means is that discrete HMM means that the observations are discrete, means 1, 2, 4, 5, right, countable. And continuous means that 25.6, 61.7, 91.4, right? This is a continuous hidden markup model. So this can handle both of them. And why it's called auto? Because it automatically finds the optimal number of parameters. Optimal parameters, like how many states you have, how many mixture components you have if you decided to use the continuous hidden markup model. I don't know what's the best initial condition. As you know, HMM actually usually, HMM uses Baum-Welch algorithm, which is expectation maximization. And expectation maximization finds the local minima, not necessarily the global minima. So we need to start from different initial condition to hope that, and use some sort of cross validation, BIC or AIC, to see what's the best initial condition to get to the global minimum. All right. And the instruction is that for more information, please go over to examples that I have here. These two examples, and the license, the software is released under MIT license, means that you are free to download this software, modify, do anything you like with that, but as long as you actually cite this paper. All right. So now I want to actually go step by step how to use this software. All right. So the step by step explanation of this package is going to be as follows. I'm going to first go here. So the name of the package is hidden markup model. I call it HMM, but in Python, this is the name of package, right? So this is the init module here. You can leave it empty, and it's going to be perfectly fine. So every time you import the package, the content of init module is going to be executed. Then so here you put the packages, or you put the classes that you want to actually run. You can also leave it empty and put it inside the different module here, right? And then let's go over this now. I'm gonna spend time on HMM.py. This is for the continuous HMM, and DHMM is for actually discrete one. All right. So there you go. First is from hidden markup model import star. It's asterisk. It's not a good practice. I did this one for simplicity, right? You can just say that from hidden markup model import, I don't know, GMM HMM or Gaussian HMM. I imported everything actually from that init module that I showed you, right? So first we start with class HMM. Later on, you see it's going to be a parent class for us. Now, perhaps the most important thing here is the init, because when we go to the Jupyter notebook and we want to execute this package and show you how this works, we need to instantiate an object. When you instantiate an object, you pass the content of this init. All right, great. So here's the train ratio is the percentile. Think about this, or the fraction of the data that is used for training. If the data is 5,000 by 10, means 5,000 observation and 10 points in time. If the training ratio is 0.1, this means that you use the first 50 observation for training and the next 450 for testing. All right, so that's what it says. Training ratio is 0.5. Let's say, for example, or 0.1, and then 1 minus 0.1 is going to be 0.9 for testing. Covariance type, if you are in the HMM one, means that for continuous HMM, and we model the observation using either Gaussian HMM or GMM HMM. So what this means is that you are going to use for the Gaussian variable, random variable, you need the covariance matrix, for example, in general, and for more than one dimension. So covariance matrix can be full, can be diag, can be spherical, can be tied. So here you pass the type of covariance matrix. The package is written on top of the HMM Learn. So you can actually look at the HMM Learn website for more information about that. But the default is diag. The max state is that, all right, so what this package does is that it automatically finds the optimal number of states and optimal number of mixture components. So what you need to give to this package is the maximum number of hidden states you have in your mind. Let's say you don't know how many hidden states you have, but you say that the cap is going to be, the max is going to be 10, right? And the max number of mixture model is the same thing. So you give 10 hidden states as a maximum number and 10 mixture components as maximum number as well. And this package is going to go and find the based on the AIC, BIC to see that, for example, you have 5 hidden states and 5 mixture components. Iter is how many times your hidden Markov model is going to run, right? And then I set it to 1000. You can set it to any number actually you like. Fit is the how many features you have. If you have a univariate time series, it's going to be 1. If you have multivariate, it's going to be as many number of measurements you have. N is the number of observation, the number of rows of data set you pass. T is the number of columns. Data is the actual data set that you pass, the data frame that you pass. And flag, this is very important here. So when you, let's take an example here. So when you actually deal with, let's say, a data set that has 3 columns for 3 points in time. And let's say the data set corresponds to a student's exam. And the maximum score is 100, the minimum is 1. There is a student that got 1, 50, 100 in this 3 exam. The first one is in the beginning of the quarter, the next one is the midterm, and the last one is the final exam. When you have 3 states, when you feed this observation to HMM for a testing, for example, when you want to find the most likely sequence of hidden states, gives you 3, 1, 2. That 3 doesn't mean anything. That 1 doesn't mean anything. What HMM is not saying that, okay, you know what, the 3 corresponds to the best state, or 1 corresponds to the worst state. What this flag does for you is that it can be 0 or 1. Flag equals 0 means that the lowest observation corresponds to the best state. Flag equal to 1 means that the best observation corresponds to the highest state. So for the exam, the higher the score, the better is that. So you pass flag equal to 1. And it corresponds to the score 100 to state 3. If you have time, the lower the better, for example, and then it does the other way around. All right, great. Now the function is def state sorting exactly does what I just described. Then wrapper is, this is very important. This is for the, when you want to print the object, actually prints it in really human understandable format, and this is exactly the information that you get out of the package. With a release, this is gonna give you them the output that you want, the most likely sequence of hidden states. This is not after the training. This is actually mainly for the testing phase, right? So, and then you go AIC, BIC. This is to find the most likely sequence of hidden states to find the actual the best parameters. Right? This is done before this beta released, right? And this one is actually very important. This AIC, BIC is based on penalizing the log likelihood, and it loops over the mixture components, and also it loops over the number of states, and actually it finds the, this is the max number of states, and that's the max number of mixture component, and it will give you the combination of hidden state and mixture component that results in the lowest BIC, all right, or the lowest AIC. Great.
Now, this is the best PIC. This one so gives you all the possible combination of the AIC, BIC. This best PIC gives you the one that corresponds to the mixture component or the hidden number of hidden states correspond to the lowest BIC. Then you go to the best state. You actually run the Viterbi list here. So this best state actually gonna go ahead. So first, when you run the HMM for that student example that I gave you, 1, 50, 100, HMM give you 3, 2, 1. After you run this the best state, it's gonna actually make it to 1, 2, 3 in a format that you like based on the flag. So this is gonna run this. Where is this? No, not this one. This is going to run this def Viterbi list. Maybe I can show it here to you as well. There you go, Viterbi list. All right, great. Now, up to now, we had an unsupervised HMM, but I want my package to contain everything. I actually wrote my first package in R, in MATLAB actually. Then I wrote it in R. Then I wanted to imitate everything that I did in R and Python, R and MATLAB in Python. And this is a supervised version, which is actually inheriting from the parent class. But the AIC-BIC function is different. Why? Because now we don't need to know about the number of hidden states, the max number of hidden states, because we already know that. It's already in the training data. For each observation, we have a corresponding labels. All right, so we don't need to loop over the number of hidden states. We only loop over the maximum number of mixture components. All right, and then the wrapper also is going to be slightly different. So besides that, everything is inherited from the parent class. That's as easy as you can get. All right, so this is for the HMM class. For the DHMM, everything remains the same. The number of symbol we have, there is no covariance type anymore. The number of symbol in the observation, right? Remember now the observation is countable. So if you have 1, 2, 3, 4, and 5 is the maximum number that you have, the number 5, you have 5 symbols actually. All right, and then everything actually very much is the same. The DS state sorting in the discrete state sorting, what is very similar to a state sorting that you saw for the continuous case. And pretty much everything actually remains the same. So we have a supervised version of the DHMM as well. DHMM is when the observation of discrete. All right, so now I'm gonna switch to Jupyter Notebook and tell you how to execute this package. All right, thank you. Perfect. So remember I had it in documents, and then I had it, where did I have it was auto HMM. There you go, it was auto HMM. And what I'm gonna do here is that I'm going to create a Jupyter Notebook here from scratch, Python 3, and I'm gonna call this one HMM practice. All right, I'm gonna call this one HMM practice. And the way it's gonna work here is that I'm gonna go here in the HMM practice. I'm gonna take this, copy this one, and paste it here. Because I found Jupyter Notebook to be better for tutorial and showing what's going on. All right, great. So everything is good here. I want to just show you about talk about a couple of important things. One, when you look at this two line, what it says is that, hey, go to the init and import everything that I have in init. This is, anytime you use asterisk is not a good practice. So it says that go to the hidden markup model .html, right? What I mean by that is this. Go here, go into this .html and import everything I have here. What do I need everything here? Not really, I only need this. So you can just go ahead and replace this by that if you want. All right, that's gonna be good as well. All right, so then I am importing a time. Why do I import it twice? And then I just want to see how long it takes for my package to run. That's the whole point of that. It's not really important. This the start time and end time. They are not really important. They are not doing anything for you. The training ratio, let's put it equal to, I set it to 0.1 because it takes less time to run. Otherwise, you don't want to have only 10% of your data for training. So we can set it to 0.8, for example. The covariance type, I set it to be diagonal. The maximum number of states, I set it to be 3. The maximum number of mixture component 4, 1000 iteration. I have univariate time series, 2000 observation overall. 50 is the length of time. Flag 1, I want the highest to be better, the highest state to be better. Path to the CSV file. All right, I'm going to show you actually some of the synthetic data that I created for myself. So I'm going to show you the structure of that. And here we're going to read the data. And remember the init that I showed you? Oh, what is this? Notebook change. On this, since the last time we opened it. All right, so overwrite, why not? I don't remember even I opened this one. What do you mean? Notebook change. Yeah, anyway, so that was a weird one. Or perhaps one of the things that I'm going to kill is this one. Oh, yes. But I'm keeping opening this actually. This thing. All right. No worries. So another thing is that what I'm doing here is that I'm instantiating this and I'm passing whatever you saw in that init that I showed you, besides the self, of course, right? And here I'm finding the best states for the HMM. So I have to go over this with you guys. Now, I have created some synthetic data for myself, actually, to show you what's the structure of the data. Let me show you here. DBM is dynamic Bayesian network. All right, let me show you what I mean by the structure of the, yeah, this is a data that I want to show you. All right, so that's how it looks like. You have in the rows, you have the observation. Assume this is the exam score for different students. This is synthetic, right? And the length of time is 50, from 0 to 49, right? So any data set you have, you're going to make it like this, in this form. And when you use that training ratio to be 0.1 out of 50,000, then it's going to choose the first 5,000 rows for training and the rest of them for testing. All right, it's great. So what I'm going to do here now is find the address, give the address of these here. And remember, we need to put 2 slash here. All right. Good. All right, so we're done. We're good. We're good to go. And everything else looks correct. Everything else looks good. And 2015, and let me just run it for you. Now I should actually count it for you. There you go. One mixture component is over. And this is actually part of the, I had a printf statement that tells you just track the progress of the package. How many states the mixture component should be over? 4. Right, so that's how you know that you're about to be done with the modeling or not. And this n and this training ratio actually determines how long it takes for your package to run, how long it takes for your model to run. The tree. And after that, I'm going to show you what I mean by the most likely sequence of states, and what I mean by having that wrapper REPR. Why did I use that inside my code? All right, so just let's copy this object. Whenever it's done, I'm going to show you this.
I'm going to show you how you can actually take a look at any other functionality this package has. It tells you how long it takes for the package to run. I actually choose the training ratio to be smaller because it takes longer, 4.8. Right? It's doing a lot. It's finding for maximum number of 4 mixture components for 3 states, 1000 iteration, and then we'll do the sorting for you as well based on the flag, whether it's 0 or 1. There you go. It took 107 seconds, a little more than a minute. Now, you put a dot here and you press on tab. You see all the functionality that this has. All right. So you want to see the most likely sequence of hidden states? No worries. Traj. That's for trajectory. All right. You run. There you go. This is the most likely sequence of hidden states for 3 states. Right. What's the length of this? You can see what's the length of this. Length of that is 400. Does that make sense? Yes. The training ratio was 0.8. The N is 2000. 0.8 times 2000 is 1600. So 400 is used for testing. All right, great. So now let me just go ahead and take this one, copy this one, and paste it here and just run. This tells you a lot of information about the package itself, right? So number of feature is 1, training ratio is 0.8. That's why I had that repair actually. To give you all this useful information. Number of cases 2000, covariance type is diag, number of hidden states is 3, number of mixture component is 4, right? Length of each time series is 50, number of free parameters 39. This is based on a covariance matrix, and 2 and 3, right? The best parameters, maximum, the best number of mixture component, and the number of hidden states. And you can look at anything else you like as well. You can just type and then go ahead and look at the, I don't know, best states, for example, and then look at this, right? So that it tells you this as well. You could get this one by just by looking at the object itself. I don't know. You can look at anything you like. You can look at max state, for example, 3, the max state that you give this package. You could see it here as well, the max state. Let's see what else you can do with this. You can look at the data train, you can look at data test, right? T that you gave, let's take a look at Jupyter release, what this one does, right? So this one not really doing much there, and that's why it actually gives you the, again, the repair. But by the way, this is actually very useful information. So I don't want to actually go over this, but this is very useful information. This is output of GHMM, GMM actually, for the, gives you various information about the covariance weights and also mean weights and everything like that. The weights that you have for the prior and everything like that. All right, so you can actually play with this, anything you like. Covariance type, what covariance type you choose, actually diag. So here you can see that what, and many more things actually, if you like. Test data. Let's take a look at test data. All right, so this is a test data, and this traj is the most likely sequence of hidden states corresponding to this test data. All right. So this is the most likely sequence of hidden states corresponding to this test data actually. All right, so for example, 3 is the best here, then the next one is 2, then 3. You see that actually makes sense, right? So that's for this. Now, another thing that I want to show you here is, now is enough for, you can actually play with this and see number of parameters. We saw that this was 39 something, or 39. The number of parameters you need. Why do we need number of parameters? Because we need it for BIC, right? So BIC, if you look at the formula, is actually penalizing the likelihood by number of parameters and the number of observation, right? So then many other things you can actually look at this state sorting. If you look at this,
right? So for here, it's like instantiating the object and actually looking at the object, all this. All right. So you can do the same thing for the DHMM, pretty much. If you have a continuous observation, you want to discretize that, I have a pre-processing module that does this for you using k-means, and it will do the discretization per time, or it will do the discretization across all the observation. But if you if you already have a discrete observation, just go ahead and directly use the DHMM. And if you have a continuous observation, go ahead and use this package for the actual modeling of the HMM. Please let me know if you have any question, if you have any comments, if you have a difficulty running this package. If you need any question about the modeling, I have a website. I will put a link in the description of this video. You can ask your question. It will directly go to my email, right? You can ask your question as well. If you don't know how to model your data set using HMM, if you don't know if HMM is the right approach for you or not, ask a question in my website. There is a forum. You can ask a question. You can ask a question under this video as well. If you like this video, please like the video, share it with your friends, subscribe to the channel, and stay tuned for more videos. And if you have more topic in mind, I can actually make a video about that as well. Thank you so much, and see you all in the next video.